Imagine a future where humans can hop between star systems as easily as taking a flight from New York to London. Picture boarding a spacecraft, engaging its engines, and in a flash of brilliant light, arriving at a planet orbiting a distant star in mere minutes or hours. It sounds like pure fantasy, something straight out of a sci-fi blockbuster. But what if I told you that some scientists today are actually exploring ways to make this wild dream a reality? It might seem like pure fantasy now, the realm of starship captains and imaginative storytellers. But pause and consider how many impossibilities of the past are everyday realities today. Flying in machines heavier than air, circling the Earth in space, even splitting the atom were once thought to be crazy ideas. Perhaps a couple of centuries from now, our great-grandchildren will consider faster-than-light voyages just as normal as we consider a transatlantic flight. The first step is to allow ourselves to imagine it, and then to explore whether physics will bend to accommodate those dreams. So, let's embark on this thought experiment together. We've all heard the famous refrain, "Nothing can travel faster than light." It's a rule that has been drilled into generations of physics students and sci-fi enthusiasts alike. Ever since Albert Einstein formulated his theory of special relativity in 1905, the speed of light, approximately 300,000 kilometers per second, or about 186,000 miles per second, has stood as the ultimate speed limit of the universe. According to what we know, you can get close to that limit, but you can never quite reach it, let alone surpass it. So far, every experiment we've done has confirmed this cosmic speed limit. Particles in giant accelerators have been pushed to 99.9% of light speed and still couldn't break that barrier. Even light itself always travels at light speed, naturally, and we have never observed anything moving faster. In fact, even our everyday technology, like GPS satellites, proves relativity right, without accounting for the slight time warps they experience, because they're moving fast and orbiting in Earth's gravitational field. Our navigation systems would drift off course. Relativity is very real, and so far it has stood firm against all challenges, especially regarding that cosmic speed limit. So why do I, and many others, dare to even think faster than light travel, FTL, might be possible? Are we just hopeless dreamers ignoring Einstein? Not exactly. We fully respect Einstein's work. In fact, it's because we understand relativity that we're looking for clever loopholes rather than trying to brute force our way past light speed. Think of it this way. If a door is locked, you can either keep ramming into it, which might be futile if it's bolted shut, or you can look for a key. When it comes to FTL, brute force acceleration ramming against nature's door doesn't work. The door of light speed is bolted by the laws of physics. But maybe, just maybe, there's a key hidden somewhere in those laws. A way to unlock faster than light travel without breaking the universe's rules. Before we go hunting for those keys, let's understand why the light speed barrier exists in the first place. In simple terms, Einstein's special relativity says that as you go faster, weird things happen to space and time. Time actually slows down for you relative to the outside world, and objects, from the perspective of an outside observer, get heavier as they speed up. The closer you push toward light speed, the more extreme these effects become. If you somehow try to accelerate a spaceship to 100% the speed of light, the math says you'd need an infinite amount of energy, which of course is impossible. It's like a cosmic asymptote. You can approach the speed of light more and more, but you never actually reach it because the universe keeps raising the price as you get closer. In everyday terms, imagine a video game where every time your character runs faster, The game multiplies your weight, so it becomes harder and harder to increase your speed. Eventually, you'd need an infinite boost to hit a certain speed. Game over. That's essentially what nature does as you approach light speed. There are other reasons nature doesn't let us break the light barrier, and they have to do with cause and effect. Basically, the logic of time itself. If something could go faster than light, in theory, it could cause an event before the cause happened, messing with the order of time. It sounds crazy, but the equations of relativity show that faster than light travel might allow for scenarios where you send a message to your own past that leads to all those famous paradoxes, the kind you see in time travel movies. For instance, the grandfather paradox, where someone could, in principle, go back in time and prevent their own existence. It's as if the universe has a big no trespassing sign at the speed of light to protect the sensible order of time and causality. So, both the practical side of needing infinite energy and the deeper side of preserving causality give us good reasons to believe that you just can't break that speed limit under normal circumstances. Under normal circumstances, that's the critical qualifier. What if we change the circumstances? What if there's a clever way to cheat, where we're not technically running faster than the speed limit, but instead changing the racetrack? Over the past few decades, scientists have been exploring exactly that. Clever tricks and loopholes in physics that might allow effective faster-than-light travel without locally breaking Einstein's laws. It's a bit like bending the rules rather than breaking them outright. Before we dive into those wild ideas, let's take a moment to appreciate why the whole notion of FTL travel is so alluring in the first place. Space is vast, ridiculously vast. Our nearest neighboring star, Proxima Centauri, is about 4.24 light years away. That distance means that even a beam of light, the fastest thing in the universe, takes over 4 years to get there. For a spacecraft like Voyager 1, which is currently coasting through interstellar space at about 17 kilometers per second, reaching Proxima Centauri would take tens of thousands of years. That's longer than all of recorded human history. Even our fastest ever space probe, NASA's Parker Solar Probe, which has hit incredible speeds, close to 700,000 kilometers per hour as it swings by the sun, would need over 6,000 years to get to that nearest star. And Proxima Centauri is in our cosmic backyard. The Milky Way galaxy spans 100,000 light years across. And there are billions of other galaxies beyond our own without some form of FTL. Our options for reaching even these nearest stars are bleak. We might have to resort to generational ships, where multiple generations live and die aboard a slow-moving starship en route, essentially committing a colony of people to a one-way, centuries-long voyage. Another idea is to place crews in suspended animation or cryosleep for millennia to awake far in the future at their destination. These scenarios feel almost as fantastical as FTL itself and underscore why a true faster-than-light solution is so enticing. It would sidestep the need for such extreme measures. One more consolation prize that Einstein's physics offers. If a spacecraft could travel at a significant fraction of light speed, time dilation would make the trip seem shorter for those on board. For example, astronauts traveling at 99.9% of C to a star might experience only a few years of travel time, even if decades pass back on Earth. In effect, they would arrive having aged much less than people who stayed behind, a kind of one-way leap into the future. But from Earth's perspective, the journey would still take all those decades, and communication with home would still be limited by light speed. So while high but sub-light speeds can ease the burden on travelers, they don't truly solve the problem of slow interstellar transit from a broader viewpoint. Science fiction has offered many imaginative solutions, Warp drives, hyperspace jumps, wormholes that instantly connect two distant points, teleportation devices, you name it. If you're a sci-fi fan, you're probably familiar with the iconic scene. The crew on the Starship Enterprise hears the command, "Engage." Stars stretch into starlines, and boom, they're at warp speed, crossing unimaginable distances in the blink of an eye. Or the Millennium Falcon from Star Wars jumping to hyperspace with a flick of a lever. These scenes captivate us because they take the vast, unbridgeable distances of space and shrink them down to something a hero can traverse in a single episode. They give us hope that someday, the universe might not be so impossibly out of reach. Now, here's the exciting part. Those childhood dreams of zipping through the galaxy at superluminal speeds inspired a lot of real scientists to start asking, could any of this actually be done? Is there any way to beat or sidestep the speed of light? And surprisingly, the answer might be yes, if we get creative enough. We can't just put a bigger engine on a rocket and gun it past light speed. That won't work. But we might be able to exploit some loopholes in physics that let us travel to distant places faster than light would normally take, without locally breaking the cosmic speed limit. One of the most promising and talked about concepts for FTL travel is the idea of a warp drive. The term warp drive comes straight from Star Trek, but the science behind it, or at least a rough sketch of the science, took shape in the real world in 1994. That year, a physicist named Miguel Alcubierre published a paper proposing a mechanism by which a spacecraft could effectively achieve faster than light travel without violating Einstein's relativity. Sounds like a magic trick, right? Here's how Alcubierre's idea works, in a nutshell. Instead of thinking about moving the ship through space faster than light, which we know is a no-go, think about moving space itself. Space, according to Einstein's general relativity, can stretch and warp gravity, for example, isn't a force pulling objects through space so much as it is objects following curves in the warped fabric of space-time. Space can expand, contract, and bend, and general relativity doesn't put a hard speed limit on the fabric of space itself changing. In fact, we know from cosmological observations that the universe has expanded faster than the speed of light in the past. During the brief period after the Big Bang, known as inflation, space itself expanded so fast that regions of the universe were pushed apart much faster than light could travel. And even today, distant galaxies are moving away from us with apparent speeds faster than light due to the expansion of space. So the idea is, if space can do that, maybe we can harness that quirk for travel. Alcubierre's warp drive concept involves creating a bubble of space-time around a spacecraft. Imagine the spacecraft sitting in its own little cozy region of space, like being inside a sphere or football-shaped bubble. The trick is to manipulate space-time so that space itself contracts in front of the bubble and expands behind it. If you can do that, the bubble of space, with the ship inside, would get pushed forward like a surfer riding a wave inside the bubble. From the ship's perspective, you're not really moving much at all. You're kind of just floating in that local pocket of space-time, so no relativistic effects fry your crew. You're not accelerating in the usual sense, so you don't feel intense g-forces. But to outside observers, that bubble of space could zip across the galaxy at arbitrarily high speeds, carrying the ship with it. Here's a popular analogy. Think of those moving walkways, conveyor belts, at airports, sometimes called travelators. You can be walking at your normal speed on the moving walkway, but relative to the ground, you're moving faster because the walkway itself is carrying you forward. If you could make that walkway move arbitrarily fast, you'd appear to zip along faster than you could by walking alone, but you still feel like you're just walking normally. Alcubierre's idea is somewhat like putting your spaceship on a segment of moving walkway made of space itself. You're not running to break the speed limit. The walkway, space, is doing the work. Another analogy that's often used is the tablecloth trick. Imagine space-time as a tablecloth. If you pull the cloth, an object on it will move relative to the table without you having to propel the object itself. Warp drive is like yanking the fabric of space to move things around, rather than blasting the object through space. It all sounds amazing on paper, and it was a huge deal that mathematically, such a solution to Einstein's equations existed. However, there was a big catch. To make space contract in front of the ship and expand behind, Alcubierre found that you'd need some truly exotic stuff. Specifically, negative energy or exotic matter with negative mass. Under known physics, you can't just have negative mass. There's no chunk of stuff you can hold in your hand that falls up instead of down, for instance. However, quantum physics does allow for some odd situations where energy can effectively be negative in a small region. The Casimir effect, for example, can produce a tiny area of negative energy density between two closely spaced metal plates. But this is a microscopic quantum effect. Creating something like that on a macroscopic scale and in enormous quantities is another matter entirely. And how enormous are we talking? When Alcubierre calculated the energy requirement for his warp bubble, it came out mind-bogglingly huge. To create even a tiny warp bubble, just a few meters across, the amount of negative energy you'd need was equivalent to the mass of the entire sun, if not more. That's completely beyond anything humanity could ever dream of producing. It was basically a polite way of the equation saying, "Nice try, but this isn't going to be feasible." On top of that, containing and shaping that negative energy into a ring around the ship, as the design required, was another seemingly impossible task. So for a while, warp drive was seen as a beautiful idea that just couldn't be practical. The theoretical possibility was there, but nature's price tag in energy and exotic matter was astronomical. However, this wasn't the end of the story. One thing about scientists, especially the ones who grew up on sci-fi, is that they don't give up easily on a cool idea. Over the years, since 1994, various researchers have been tinkering with the warp drive concept, trying to see if there are ways to lower the energy requirements and get rid of the need for truly exotic matter. One of those researchers is Dr. Harold Sonny White, a NASA engineer who became well known for his work on advanced propulsion concepts. In the early 2010s, Dr. White revisited Alcubierre's equations and made a few tweaks. He found that by altering the geometry of the warp bubble, essentially making the shell of the bubble thicker and oscillating the warp field, the energy requirement could potentially be brought down dramatically. Instead of needing the mass energy of a star, maybe you could do it with something like the mass of a large asteroid, or, by some claims, even just a few tons of exotic matter. When this was first reported, it sounded almost too good to be true, and it may well have been optimistic. But the key point was, the community started realizing that maybe the warp drive wasn't quite as impossible as initially thought. Perhaps our first calculations were overly pessimistic, and with clever engineering of the space-time geometry, the impossible could inch closer to the realm of barely possible. NASA even set up a modest research effort at Eagleworks Laboratories' Johnson Space Center to experimentally test small warp-related effects. They devised what's called a White-Juday warp field interferometer, an apparatus to detect tiny distortions in space that a warp field would cause. Basically, trying to create and measure a microscopic warp bubble in the lab. Now, to be clear, they weren't anywhere near zipping objects around. This was just a proof of concept to see if space-time could be bent in the Alcubierre way on a very small scale. Over the years, there were rumors and premature news articles claiming things like NASA scientists have observed a warp bubble in the lab. But the reality is that this research is extremely challenging, and results have been inconclusive so far. However, even attempting such experiments shows how far we've come from dismissing warp drive as pure fiction. Another development came in 2021 from physicists Alexei Bobrik and Gianni Martire. They took a fresh approach to the warp concept. Instead of directly modifying Alcubierre's design, they started from scratch with the physics constraints and tried to derive a physical, as opposed to purely mathematical, warp drive model. They published a paper outlining a model for a warp bubble that didn't require any negative energy at all. The catch? Their solution could only achieve subliminal, slower than light, speeds. Essentially, they found a way to make a warp bubble using known physics, meaning no exotic matter. But it wouldn't break the light barrier. It was more like a futuristic, super-efficient slow warp. While that might sound less exciting, it was actually a significant step. It meant we were learning how to describe warp bubbles in more realistic terms, and any progress in that understanding could eventually lead to the big prize. A true FTL warp drive that is physically achievable. Hot on the heels of that work, interest in warp drive research has grown. By the mid-2020s, even some mainstream scientists who used to roll their eyes at the mention of warp drives have started paying attention because the theoretical groundwork is firming up. In 2025, a group from the Advanced Propulsion Laboratory, which includes some of those earlier researchers, announced a new concept for a fully physical warp drive. This design again claims no need for negative energy and instead involves what they describe as floating bubbles of space-time. Without diving into the technical nitty-gritty, the basic idea is to create a stable bubble that moves itself through space-time, sort of like a self-contained warp bubble that doesn't rely on weird physics outside what we already know. The scientists involved, and even Miguel Alcubierre himself, who gave it a thumbs up, cautioned that this is still all theoretical. We're not about to get a warp drive spaceship next year, or even next decade. The energy required is still enormous, though a lot less than the mass of the sun apparently. And we have no clue how to engineer something like this yet. But the big shift is that warp drive moved from just a mathematical quirk that probably isn't real to this might actually be possible someday if we can figure out the tech. That's a huge leap in optimism. In fact, in 2021, Dr. White and his colleagues published a paper suggesting that a properly shaped tiny structure on the scale of nanometers could theoretically produce a very small warp bubble effect in the vacuum. This was a numerical finding. They didn't create one in the lab yet, but it hinted that the warp concept might be more than just equations on paper. Even though a nano-sized warp bubble is a far cry from a starship, it is an encouraging hint that space-time can be manipulated in subtle ways. Let's take a step back for a moment. So far, we've been talking about warping space to travel faster than light indirectly. That is, you're not moving through space faster than light. Space is carrying you. There's another major concept for faster-than-light travel that's been popular in fiction and theoretical physics: wormholes. If warp drive is like riding a wave of space, a wormhole is like taking a tunnel or a shortcut through space. A wormhole, also called an Einstein-Rosen bridge in the context of general relativity, is basically a bridge or tunnel connecting two separate points in space-time. Think of the classic analogy. Imagine the universe is a big sheet of paper. You are at point A on one end of the sheet, and you want to get to point B on the far end of the sheet. Normally, if you're an ant walking on the paper. You have to trudge your way across the 2D surface from A to B. That could be a very long walk if the paper is large. But if you could fold the paper so that A and B touch, then you could just step from A to B instantly. A wormhole is like punching a hole through the folded paper so you can jump between those 2 points without traveling across the intervening surface. General relativity actually allows for the mathematical possibility of wormholes. In fact, the equations of GR, the theory of gravity that Einstein published in 1915, say that if you have a black hole, a region of space where gravity is so strong, not even light can escape, and its weird mirror opposite called a white hole, kind of the reverse of a black hole, which basically spits things out and nothing can enter it. You could join them and create a passage, a wormhole. Now, we have lots of evidence that black holes exist in the universe, but white holes, not so much. They appear to be purely theoretical. We've never seen one, and it's hard to imagine how one would form naturally. And even if you had a pair, the wormhole they create would be outrageously unstable. It would tend to pinch off, collapse, or basically destroy anything trying to go through it almost instantaneously. So naturally, scientists thought, how could we make a wormhole traversable, that is safe, or at least possible, to travel through? The answer, unfortunately, again comes down to that pesky requirement for exotic matter with negative energy. To hold a wormhole open and keep it stable, you'd need something that pushes space-time outward against collapse. Negative mass/energy stuff can do that in theory. If you could line the throat of a wormhole with a kind of negative energy scaffold or use cosmic struts of exotic matter, you might keep the tunnel open long enough for a spaceship to fly through. Without that, gravity is going to pinch it shut and possibly unleash some nasty radiation in the process, which would vaporize you if the collapse doesn't get you first. Assuming, for a moment, that we solve that problem and a traversable wormhole could be constructed or naturally found, what would traveling through one be like? It could be like stepping through a portal. You enter the mouth of the wormhole here and pop out perhaps on the other side of the galaxy, or in another galaxy altogether, almost instantaneously. It's essentially the ultimate shortcut. Unlike warp drive, where you're actually covering the distance, just in a tricksy way by bending space. With a wormhole, you kind of circumvent distance entirely by connecting two faraway locations directly. Wormholes make frequent appearances in fiction as well. If you've seen the movie Interstellar, a wormhole near Saturn allows the heroes to travel to another galaxy in no time at all. In Stargate, the film and TV series, wormholes are created artificially to hop between planets. The idea is incredibly tantalizing. It's like the universe's version of a subway system or an express elevator. But right now, wormholes are even more speculative than warp drives. At least with warp drives, we have specific equations and designs we're fiddling with. With wormholes, the big elephant in the room is we have zero evidence that any kind of exotic matter or negative mass exists to stabilize them. Plus, even if it did, actually engineering a wormhole, manipulating a black hole or space-time geometry, is far beyond us. There's also a wild implication of wormholes. If you could travel through space so quickly, you might also inadvertently create a time machine. This is where wormholes and warp drives both get into a bit of trouble. Under relativity, if you can go faster than light in one frame of reference, it turns out you can actually go back in time in another frame. With wormholes, if you move one end of the wormhole, say, you hold one mouth around at high speed and bring it back, a bit like the twin paradox, scenario in relativity, you could end up desynchronizing the two ends in time. That means someone could enter a wormhole and come out, not just somewhere else in space, but potentially at an earlier time. You could have situations like going through the wormhole and arriving before you left, opening the door to time paradoxes. Some scientists, like Stephen Hawking, suspected that maybe some fundamental law we don't yet fully understand, sometimes called chronology protection conjecture, prevents these paradoxes from ever happening. Essentially, that the universe might self-censor anything that would allow backwards time travel. This could mean that any attempt to make a true FTL wormhole or warp drive that allows time travel would ultimately fail due to quantum effects or something we haven't discovered. But all that is still in the realm of speculation. The bottom line is, wormholes are a conceivable loophole for faster-than-light travel, but they come with their own hefty baggage and uncertainties. As of now, we have no idea how to obtain the required negative energy on a scale larger than tiny quantum phenomena. And without it, wormholes, if they exist at all, would be untraversable, one-way trips to oblivion. Some theorists have even speculated that tiny wormholes might exist at the subatomic scale, constantly appearing and vanishing in the quantum foam of space-time. If that's true, and it's purely conjecture at this point, a sufficiently advanced civilization or technology might conceivably grab one of those microscopic wormholes and enlarge it into a macroscopic tunnel. It's a wildly speculative idea, but it shows how far people are thinking outside the box when it comes to shortcuts through the cosmos. While warp drives and wormholes are two of the headlining ideas when it comes to FTL, there are other more exotic or subtle concepts that often get mentioned. Let's touch on a few tachyons. These are hypothetical particles that always travel faster than light. They popped up as a concept in the 1960s from the equations of special relativity. Basically, if particles with normal positive mass, sometimes called tachyons, or just ordinary particles, are limited to below light speed, then what about particles with imaginary mass? Those would be tachyons. Tachyons, if they exist, would have the strange property that they slow down as they gain energy, the opposite of normal matter. And to stop a tachyon, bring it down to light speed, you'd need infinite energy. They also would mess with causality big time. A tachyon sent as a signal could be received before it was sent, in some reference frames. Now, tachyons have never been observed. Pretty much all physicists think they probably don't exist in reality, because they would violate causality and create all sorts of logical problems. Occasionally, in particle physics theory, you'll hear the term tachyon when describing certain fields, like if an equation has a solution that seems to imply imaginary mass. But usually, that's a sign of an instability in the theory, rather than a real faster-than-light particle zooming around. Tachyons are fun in fiction, and the word gets dropped a lot in sci-fi techno-babble to explain superluminal signals or time travel. But as far as we can tell, nature has not been caught using any tachyons. Hyperspace and extra dimensions. Another idea often floated in theoretical physics and science fiction involves extra dimensions beyond the familiar three of space. Some theories, like certain models in string theory, suggest there could be hidden spatial dimensions. If one could enter a higher dimensional hyperspace, the constraints of our normal space might be bypassed. A ship might pop out far away without locally breaking light speed. This is the classic hyperspace jump idea in many sci-fi stories. Currently, we have no evidence we can actually do this. If extra dimensions exist, they seem inaccessible to us, except perhaps in exotic circumstances. They might be curled up tiny or require immense energy to utilize. But it's an intriguing notion. The true structure of the universe could conceivably allow shortcuts we haven't yet discovered. It's another reminder that future breakthroughs in fundamental physics might open doors we don't even know are there. Quantum tunneling and quantum entanglement. These are two phenomena from quantum physics that people sometimes mistakenly think can transmit things faster than light. Quantum tunneling is when a particle manages to pass through a barrier that it seemingly shouldn't be able to, like a ball tunneling through a hill instead of going over it. There have been experiments that measure how tunneling happens, and in some cases, it appears as if the particle traversed the barrier faster than light would, almost as if it took a shortcut. However, detailed analysis shows that you can't actually send a useful signal or object faster than light using tunneling. The particle's wave function has a small part that leaks through the barrier, but you can't control it in a way that breaks causality. It's a bit like having a very slim chance of something spontaneously appearing on the other side of a wall. You can't use that to reliably send a message or yourself through faster than light because it's fundamentally probabilistic and doesn't carry information in a controllable way. Quantum entanglement is another weird one. If two particles are entangled, measuring one instantly affects the state of the other, no matter how far apart they are. Einstein famously referred to this as spooky action at a distance. It sounds like magic. You do something here, and something instantly happens light years away. But here's the rub. Entanglement can't be used to send information by itself. When you measure one entangled particle, you get a random result, and the other particle will have a correlated random result. To make any sense of what happened, you still need to communicate normally, at light speed or slower, with whoever has the other particle to compare notes. In other words, entanglement is like having two dice that are guaranteed to always show the same number when rolled, even if they're far apart. You roll your die and get, say, a 6. You instantly know the other person's die is also showing 6 at that moment. But neither of you gets to choose what number appears. It's random. You can't send a message like 6 means attack now, because you didn't have control over getting that 6. It just came up. You only know after the fact what it was, and to communicate any actionable information, you still need a classical channel, a phone call, radio message, etc., to say, I got a 6. Did you get a 6? Yes? Okay, interesting. Thus, entanglement doesn't allow superluminal communication. It's super weird and fascinating, but it doesn't help us break the light barrier in terms of travel or sending signals. For instance, scientists have even performed quantum teleportation experiments where the quantum state of a particle, like a photon, is transferred to another distant particle using entanglement. In 2017, for example, a team in China teleported a photon state to a satellite in orbit. This was hailed in the news as if they teleported the photon itself to space. But in reality, no physical particle traveled faster than light. The trick still required a normal signal to complete the teleportation process. So, even quantum teleportation, despite the sensational name, obeys the cosmic speed limit. Now, speaking of signals, it's worth mentioning that faster-than-light communication is essentially the same problem as faster-than-light travel in terms of physics violating causality. If you could send information faster than light, you could potentially send information to the past. Just like an object going ft could appear to some observers as going back in time. So far, we have never seen any evidence of causality violation. Every experiment upholds that cause comes before effect, and nothing observable travels faster than ZC. Even the subtle tests of entanglement, when carefully analyzed, preserve this order. No usable info goes FTL. You might recall an interesting incident from a few years back that illustrates how ingrained the light speed limit is in science. In 2011, a research collaboration called OPERA, based in Italy, was studying neutrinos, those ghostly subatomic particles that zip through matter. sent from CERN in Switzerland. They made a shocking announcement. Their measurements suggested that neutrinos had arrived at the detector slightly earlier than light would have, effectively hinting they might have gone faster than light by a tiny fraction of a percent. It was a tiny difference, like 60 nanoseconds faster on a trip of 730 kilometers. But if true, it was earth-shattering. The news made headlines worldwide. Had Einstein been wrong? Could neutrinos break the speed of light? But guess what? Nearly everyone in the physics community was extremely skeptical. Why? Because extraordinary claims require extraordinary evidence. And every other piece of evidence we had said, AFTL is not possible. Sure enough, after months of scrutiny, it turned out it was a measurement error. A loose cable in the experiment's timing system, of all things. When they fixed that, neutrinos behaved just like good citizens of the universe and obeyed the speed limit. This episode was a great demonstration of how seriously we take the light speed rule. Even the tiniest hint of a violation was investigated exhaustively. And in the end, Einstein's relativity emerged unscathed. So, reality check. As of now, no one has seen anything go faster than light or any signal sent that breaks that barrier. All these concepts, warp drives, wormholes, tachyons, etc., remain theoretical or speculative. However, we're in an exciting era where these ideas are no longer just fringe science fiction. They are being actively researched by physicists, and incremental progress is being made toward understanding if FTL travel might be achievable under the laws of physics. Let's summarize the big challenges that any method of FTL travel must overcome. First and foremost is energy. Every scheme we've looked at requires mind-boggling amounts of energy, whether it's mass energy equivalent to a planet to warp space-time or the energy to create exotic negative mass particles. The numbers are staggeringly beyond our current capabilities. To put it into perspective, the energy humanity uses in an entire year is just a tiny flicker compared to the power of the sun. In a single second, our star releases more energy than all of human civilization consumes in hundreds of thousands of years. It's a reminder of how unimaginably vast the scales of energy are when we start talking about the mechanics of light speed and beyond. And even that pales in comparison to some of the energy figures thrown around in warp drive equations. So, any hope of FTL will likely require breakthroughs in how we produce and harness energy. We might need something like matter-antimatter annihilation engines, the most energetic reactions we know of, or tapping vacuum energy, or harnessing the power of black holes, or something extremely exotic. The second challenge is materials/technology. Even if the theory is sound, engineering it is another story. For warp drives, you'd need a way to shape and contain fields of extreme magnitude, something far beyond anything, like the magnets in our particle accelerators. For wormholes, you'd need materials we've never seen, negative mass stuff, and the ability to manipulate neutron star-like densities. We might be talking technology thousands of years ahead of us, or maybe never. We just don't know. But remember, people once said that heavier than air flight was impossible, or that going to the moon was a lunatic dream. So we should be careful not to declare something impossible for all time, just because it's hard. But it is fair to say it's tremendously challenging. Another issue is safety and control. Suppose you had a warp drive that could go to 10 times the speed of light. How do you navigate? How do you avoid running into anything? If you're warping space, you might also warp light around you. Could you even see where you're going? There have been musings about warp drives potentially creating devastating effects when they arrive somewhere, like releasing bursts of high-energy particles. Some studies suggested that if a warp bubble decelerates, it might release all the particles gathered during the journey in one intense flash, frying the destination. These are very speculative, but they underscore that even if we can do FTL, we'd have to be extremely careful in using it. With wormholes, the concern is, what if it collapses while you're inside? That would be an instant crush to oblivion. Or what if using one causes some unforeseen cosmic consequences, like creating a dangerous radiation or a black hole? When dealing with such extreme physics, we have to consider the side effects. Another practical concern: space might be mostly empty, but it isn't completely void of material. At extreme speeds, even stray atoms or dust particles become dangerous. A grain of sand hitting a spacecraft at near light speed would release energy comparable to an explosion, potentially catastrophic. How could a starship be protected? Perhaps a strong magnetic field or a plasma shield could deflect particles, or a warp bubble itself might push aside debris as space is distorted. These protective measures are an engineering challenge we'd have to solve. Science fiction often glosses over this, but any real FTL craft must reckon with the harsh reality of interstellar space hazards. Then there's the causality paradoxes we touched on. If nature truly allows FTL in any form, does it somehow prevent the paradoxes? One possibility is that all FTL schemes still can't send information to the past once quantum effects are considered. Some theoretical physicists have suggested that quantum physics might save the day by forbidding the kind of closed time loops that would cause paradoxes. But until we have a theory of everything that combines quantum mechanics and general relativity, this is an unresolved question. It's possible that a theory of quantum gravity will put new constraints on things like warp drives or wormholes. Or it might reveal new possibilities we haven't even imagined yet. We are still missing pieces of the puzzle when it comes to gravity at the quantum level. Considering everything, you might wonder, so what's the verdict? Is faster than light travel truly possible or not? The most honest answer from a scientific standpoint is, we don't know. Not yet. What we can say is that conventional means, rockets, etc., definitely can't do it. We'd need some breakthrough in our understanding or application of physics. The encouraging thing is that no law of physics explicitly forbids the concepts of warp drives or wormholes. They're extreme solutions to Einstein's equations, but they are solutions that means our current theories at least leave the door open a crack. However, not forbidden is a far cry from actually achievable. Here's what's true and what isn't, as best we know. True, no object or information has ever been observed traveling faster than light in a vacuum. Special relativity has been tested over and over, and it holds up perfectly in all experiments to date. True, if you try to just accelerate a normal object past light speed, you will fail. Nature will throw up infinite resistance as you approach C, and you'll never get there. True, concepts like warp drives and wormholes don't directly contradict relativity. They sort of get around it by taking advantage of general relativity's flexibility with space-time, or by postulating exotic conditions. Not proven. We have no experimental evidence that warp drives or wormholes can actually exist. We have theory papers and mathematical models, but no physical warp field has been produced that we can definitively say is real, and no wormhole has ever been seen or made in a lab. Not true, as far as we know, that FTL travel is easy or just around the corner. It's not. If it is possible at all, it's going to require technology and understanding far beyond what we have now. The safest stance from a scientist's perspective is, FTL travel might be possible in principle, but it's not possible for us at the moment. However, as the person making this video, and as a science enthusiast, I'll add that I think it's important we keep exploring these frontiers. Every time in history we've thought something was impossible, we later found a way. often not by breaking the laws of physics, but by finding clever ways to work within them. Heavier than air flight, breaking the sound barrier, reaching space, splitting the atom. All these seemed nearly magical before they were achieved. FTL travel is orders of magnitude tougher, no doubt. It may take a paradigm shift in physics, maybe the discovery of a new aspect of space-time or mastery of quantum gravity, or a huge technological leap like harnessing energies on a stellar scale. Those are tall orders, but not necessarily permanent deal breakers. As we stand today, we are taking baby steps. Projects like the Breakthrough Starshot are looking to push tiny probes to maybe 20% of light speed using powerful lasers, which could get them to nearby stars in a couple of decades. That's not FTL, but it's faster than anything we've ever sent before. It's an ambitious initiative that illustrates both the possibilities and limitations of our current approach. This plan involves an array of ground-based high-power lasers that would concentrate light onto a light sail attached to a tiny spacecraft, basically a microchip with a sail. The intense light pressure would accelerate this miniature probe to perhaps around 20% of the speed of light. At that velocity, the probe could reach the Alpha Centauri system in roughly 20 to 30 years. Crucially, this probe is unmanned. It's far too small for people, and the acceleration would be too extreme for a human passenger. Still, if successful, Starshot will mark the first time humanity sends something into interstellar space at a substantial fraction of light speed. It's a stepping stone, nowhere near FTL, but a step closer to bridging interstellar distances with technology. To get a sense of the challenges, consider Breakthrough Starshot, a project currently underway that aims to send tiny probes to another star at maybe 20% of light speed. The idea is to use a gigantic array of lasers on Earth to shoot a powerful beam at a spacecraft that's basically a small, ultra-lightweight light sail. The laser push would accelerate this gram-scale probe to a significant fraction of the speed of light. At 20% of light speed, the probe could reach the Alpha Centauri system in about 20 to 25 years. That's incredibly fast by our standards, but notice a few things. It carries no people. It's just a microchip with a camera and transmitter. And it requires an enormous technological effort. Hundreds of lasers, adaptive optics, etc., to achieve even that speed. This illustrates both how far our current tech is from FTL, and also the creativity scientists are employing to at least creep closer to the light speed barrier. If Starshot works, it will be humanity's first step toward the stars, albeit still subliminal, but faster than anything we've done before. Now, you might wonder, why even bother if it's so difficult? The reason is simple. The payoff would be astounding. If faster than light travel became a reality, it would arguably be one of the greatest revolutions in human history. The entire universe would open up to us. We could become an interstellar species, perhaps even an intergalactic species eventually. The things we could learn and experience. Imagine actually visiting other star systems, seeing alien worlds with your own eyes in a reasonable time frame, not just through telescopes. It would unite knowledge from the tiniest scales, quantum physics, to the largest scales, cosmology, because building something like a warp drive or wormhole generator would require understanding and mastering both. In pushing for FTL, even if we fail, we are likely to discover amazing new physics along the way. And that journey of discovery often yields benefits in unexpected ways. New technologies, deeper understanding of the universe, etc. So, I maintain optimism. Maybe it's the sci-fi geek in me, but I think if something isn't strictly forbidden by the laws of physics, then, as Arthur C. Clarke said, the only way of discovering the limits of the possible is to venture a little way past them into the impossible. It's possible faster than light travel will remain an impossible dream, always tempting us, but forever out of reach. A kind of asymptotic goal, but by daring to investigate it, we push the boundaries of what may become possible. Clark also reminded us that any sufficiently advanced technology is indistinguishable from magic. What looks like magic now could be routine in the future, with enough ingenuity and knowledge. For the time being, the stars remain very, very far away. But human ingenuity has a way of cutting down impossibilities. Today's impossible could be a routine operation for our descendants centuries hence. Perhaps one day, faster than light starships will depart Earth, and humans will look back at our planet, shrinking behind them, knowing that they are bending space or stepping through a wormhole, embarking on journeys once confined to our imaginations. Until then, we keep our curiosity alive, we keep exploring physics, and we keep daring to dream big. Because if we stop dreaming of warp drives and star voyages, we might miss the chances we do have to turn them into reality. So yes, I do think faster than light travel is possible. Not easy, not anytime soon, but possible. And even if I turn out to be wrong, chasing that possibility will lead us to discover so much more about our universe. After all, as the saying goes, magic's just science that we don't understand yet. What seems like magic today, jumping across the galaxy in an instant, might one day be just another chapter in the textbook of human achievements. Until that day, we'll keep pushing the boundaries of the possible, one experiment and one theory at a time. Safe travels, spacefarers, and thank you for coming along on this speculative journey faster than light.